Hey, welcome back to section 5.1. This is a meaty chapter, and this is the second portion of this. We've actually gone through this, but I'm going to give a synopsis of all of these rules based on the graph I created on the first one. But if you're foggy with this, you're going to want to go back for a deeper explanation to the chapter 5.1a part 1 video that was made prior, because we've been through this. So what we're looking for here are extreme values. Extreme values could be absolute extremes, such as on this blue curve. The biggest it ever is 9. On this green curve, its extreme at -4 appears to be 7. This orange curve, its tallest point appears to happen over here at like -8.2-ish or something, and it's close to 2. The red graph, its extreme minimum is down here at -8. Its extreme maximum lives in here. The green graph's extreme minimum, etc. But we also have relatives. This would be a relative minimum right here. This relative minimum is not the minimum of the red curve. The red curve goes down to 7. This is only down 5 or so. But it's called a relative minimum or a local minimum, which is the term that I should get more comfortable with. So if we're looking for these extremes, what we need to consider is endpoints. And this is assuming that all of these functions were defined, with the exception of that black one, all of these functions were defined to exist from between -10 and 10, including -10 and 10. We need to consider endpoints, and we need to consider any place where the slopes are 0. Those could be maxes, or relative minimums, or minimums. Doesn't guarantee, notice here the slope is 0, and that's neither a relative maximum, a local maximum, local minimum. It's not a maximum minimum of the graph, but it's worth finding where slopes are 0, and where we have corner points or cusps, and that's where the slopes are undefined. So if we find a derivative and it's undefined at a value in the domain of the function, then there could be a maximum value at that point, even though we can't find a derivative of it. So that is the gist of what we went through for quite a bit, building these graphs and explaining what's going on as we were going through each of these rules. We got down to this place where we talked about critical points, a point in the interior of the domain of a function at which the derivative is 0. Derivative would be 0. Here, 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 and there, or the derivative does not exist here, is called a critical point. And those critical points, there's a very, very good chance those will lead us to our relative maxes, relative mins, absolute max, absolute min, but no guarantee. It could just be what's referred to as a stationary point. So anyway, we went through a number of examples. Here they define here we define stationary point, just a leveling off point where the slope is 0. We went through a number of problems. These we've done in the first part of the video where they defined a domain for us. And to be honest, that's helpful. It means I definitely want to find what f of 0.5 is. I definitely want to find what f of 4 is, because those are the endpoints. Those might be our maximums, minimums. And almost without a doubt, they are at least a relative max or a relative min, unless the graph is completely flat. And we went through some of those. And then we got to some, well, the domain was all real numbers. And when we look at this is a right side up parabola, terrible parabola. So it has no relative maximum. It has no absolute maximum. It doesn't get to infinity, but it approaches infinity. Infinity is a concept, not a number. But it did have an absolute minimum, which was also relative to the points around it, a minimum. And once again, -infinity to infinity. And then we got to some points that this graph doesn't exist -infinity to infinity, much like here's where we made it to. This graph does not exist everywhere, but the author of this problem would not be responsible for telling us that. If the author wanted to tell us that we're only looking for values from 0.1 to 0.3, she could tell us that. But we're looking for where this entire graph exists, and I know that 1 minus x squared, because it is in a denominator, or excuse me, because it's in a radical, has to be at least 0. But because it's in a denominator, it also cannot be a 0, because square root of 0 is 0, and 1 divided by 0 is undefined. So we have to be bigger than 0. So I'm going to figure out our domain. That becomes x squared, if I add it to both sides, equals 1. So x is plus, or I'm treating it as an equal to, plus or minus 1. I'm going to go to a little chart, negative 1, 1. If I put 1 in here, it's undefined. If I put negative 1 in here, it's undefined. If I put 0 in here, it's 1. This is a good zone in here. This is a bad zone out here because if I don't know why that's backwards, negative 1, positive 1, sorry. This is a bad zone out here because if I put in 2, 3, 4, I get 1 minus something bigger than 1. Likewise, if I put in negative 2, I get square root of a negative. This is a bad zone, which means it's just implied that negative 1 is less than x is less than 1. So we're only going to look for values between those, and I don't even have to test the endpoints because they don't exist. Now back on this problem, we determined that our domain was x is less than negative 1, or x is less than or equal to negative 1, or x is greater than or equal to positive 1. You can check that and see. That means that we needed to test those values to see if they were extremes. But in this case, I'm not going to test 1 and negative 1. Okay, so far I've got no points to test. Usually we get an endpoint to consider, but the endpoint, they don't exist at negative 1 and 1. And those are the endpoints circled. Okay, let's find y prime, or if I call this f of x, let's call it f prime of x. I might want to think of this as, let's see, 1 minus x squared to the negative 1/2. So the derivative is outside derivative of the inside function times the inside derivative. Or treat the mother, leave the baby alone, treat the baby. So that becomes, I've got a negative 1 times negative 2, 2, divided by 2, 1, and an x. I get plain old x on, that's a half, so square root of 1 minus x squared to the third. So what am I interested in? One thing I'm interested in from the derivative is when the slope is 0. And the slope is only 0 when the numerator equals 0. Slope equals 0. Therefore, the numerator of the fraction equals 0. It happens at 0, provided 0 doesn't make my denominator 0. And it doesn't. And provided 0 is in our legitimate domain, and it is. So I'm definitely going to want to find f of 0. Other points we're interested in, where we might have maximums and minimums, is where the slope is not, or where we can't find the slope, or where the function is not differentiable. Well, that would occur, again, when x is 1 or negative 1. But we're not going to consider those because they're not in our domain, our implied domain, to begin with. So all we have to find is 0 and then determine, is that a maximum, a minimum, or just a stationary point? So let's see. F of 0, I get 1 on square root 1 minus 0 squared, and I get 1. So if I was graphing this right now, I would have a point here. I know at 1 and at negative 1, let's consider what happens. They don't exist, and they're not part of my graph. Is it a hole in the graph? Is it just an open circle that we go to? Let's consider what happens as I approach 1. As I approach 1, coming in from the left side, 0.999, I get 1 minus 0.999, 0.001. I get a tiny little number underneath 1, which becomes big compared to the tiny number. Oh, this is wanting to become infinity. Or take a look at an evaluation of the slope. We know the only place that the slope, this is big, focus in, rewind, listen to it if you don't get it. The only place that the slope is 0 is right here. Instantaneously, this is stationary just for a moment. If I put a positive value in here for x, I get positive over, if I put a positive value between 0 and 1, I get 1 minus something a little smaller than 1. I get a positive on positive. I know that my slope to the right of 1 is going up. I'm going up forever. So pretty well implies that we're doing this. What happens when I put a negative value between 0 and negative 1? I get a negative over, If this is between 0 and negative 1 and we square it, that's between 0 and 1. Therefore, this is still positive. I get a negative on positive. The slope is negative. That's implying, see the slope, I know my arrow's going up, but the slope is negative. Other things we could do, we could put a 1/2 in here, and we'd find out that our point is up. We could put a negative 1/2 in here, find out it's up. We might look at this graph and say, oh, it's even. Whatever it does to the right, it's going to mirror that to the left. Therefore, we have a minimum at 0 of 1. And that is an absolute minimum. It is also a relative or a local minimum as well. I mean, it is the minimum of the curve. There is no maximum. We might talk about it's approaching infinity, but we wouldn't say that the maximum is infinity. Okay, C, along those same lines, I have an upside down parabola. This thing I might want to be considering when it is less than 0, because I know that negative x squared plus 2x plus 3 has to be at least 0, and it can equal 0 now. So if I just set this equal to 0 and solve, I'm not going to deal with the greater than or equal to. I'm going to find regions and test them. Set this equal to 0. I'm going to multiply by negative 1 just because I prefer positive. If I'm doing that here, I'd have to change this to less than. You can do that if you're comfortable. I just set it to equal to 0 and then evaluate, especially when it's something as simple as a parabola. What do I know about this parabola? Ultimately, forget about the square root. That isn't the entire graph, but ultimately the parabola wants to go down. All right, we'll come back to that. So if I multiply both sides by negative 1, I get x squared minus 2x minus 3 equals 0. Ooh, that's nice. X minus 3 times x plus 1 equals 0. So x equal 3 and negative 1 are going to be pretty interesting points for me. Let's consider those for a moment. 3, negative 1. At negative 1 and 3, I get 0. That's not open circles. I'm not talking about domain right now, but I get actual zeros at that point. I guess if I was treating this like a regular old graph, here's my y-axis coming through here, those would be zeros of this thing. Okay. If I was just looking at the parabola. Turns out there are also zeros of this. Now, can I put 0 in here? If I put in 0, I get 3 plus 0 minus 0, I get 3. So this is a good zone. And then we have put in 4. Let's see, I get 3 plus 8, 11 minus 16. This is a bad zone. I can't have negatives in there. And if I put in negative 2, I suspect that's a bad zone. 3 plus 2 times negative 2, that's 3 minus 2, negative 1, minus 4. Yep, it's negative. This is a bad zone. Therefore, the implied domain is negative 1 is less than or equal to x is less than or equal to 3. Why is that important? Because that tells me that I need to find f of negative 1 and I need to find f of 3. We could do it right now. I get the square root of 3 plus 2 times negative 1 minus negative 1 squared, or square root of, let's see, that's 3 minus 2, 1. It is 0. Well, of course it's 0. That's why we did it. Likewise, square root of 3, I get 3 plus, it's good to check, 2 times 3, that's 9, minus 3 squared. Of course it's 0. That's why we did it. So those could be either maximums or minimums, and we got them on both sides. All right, let's go to derivative. We might want to look at this as 3 plus 2x minus x squared to the 1/2. We may want to think of it that way to find, if I call this f of x again, to find f prime of x. So I get outside derivative 1/2 something to the negative 1/2 of the inside function times the inside derivative, that is negative 2x plus 2. So I get, when all is said and done, this 2 is going to reduce those 2's. Half of that times 1, I get negative x plus 1. 2 reduce those, multiplied by 1, all on square root of 3 plus 2x minus x squared. Okay, I am interested in when is this 0 and when is it undefined. It's undefined when the denominator is 0. We already know the denominator is 0 at -1 and 3. So it's undefined there. So those would be some interesting points, but we're already testing them anyway. And when is the whole function equal to 0? When is the slope 0? The slope is 0 when -x plus 1 is 0, or when x equals 1. So I want f of 1. Okay, f of 1 gives me square root of, I suspect it's right in the middle of these because we have a little parabolic thing going on in there, but let's find out. I get, well, actually 1 is right in the middle of those already. I get 3 plus 2 times 1 minus 1 squared, or I get square root of 3 plus 2, 5, minus 1, 4, square root of 4, I get 2. So if I know my graph only exists here and here, if I'm setting up kind of a two-dimensional graph here, I know -1 and 3 are zeros. I know I've got a point at 2, 2, or 1, 2, excuse me, 1, 2. Does that make this a maximum, or might it level off here and go up? Well, if it levels off here and goes up and comes back down, then it would have to level off again, and it only levels off one time. So this has to be a maximum. Is it circular? Is it parabolic with the square root in there? I don't know, maybe, but I do know this. It only levels off here, and it's continuous to there and continuous to there. So we have minimums at x equals -1 and 3, because they do exist, unlike the prior problem, and those minimums are 0. And we have a relative maximum, a local maximum we could also call it, or an absolute maximum. We have a maximum at x equals 1 of 2. So if they say, what is the maximum value? It's 2. It's kind of nice to describe where it is, the ordered pair 1, 2, the ordered pair 3, 0, the ordered pair -1, 0. Okay, lots of practice on these. Let's take a look at one more. So let's talk about domain, because they didn't give me any domain restrictions. X squared cannot be -1. Oh, the domain is all real numbers. So we're going to put in all real numbers here, -infinity to infinity. So if you want to list that, -infinity to infinity, this graph exists everywhere. Okay, so first thing I want to do is I want to try endpoints, but I can't put -infinity, infinity in there. However, it might be worth considering putting huge numbers in here. As I put in huge numbers, I get huge number, but over huge number times huge number. This is going to approach 0 by the big X test, left and right. Limit as we approach infinity, and -infinity is going to be 0. That might be helpful for us to think about. All right. So let's go ahead and find y prime, or f prime of x, if I call this f of x equals. So f prime of x is low, all of it, d high, minus high, d low. I always say parentheses don't cost you a thing. All over the square of the thing below, x squared plus 1 squared. Only thing the parentheses cost you is a tiny bit of ink for these awesome Signo pens, highly recommended. Okay, so let's simplify. I get an x squared minus 2x squared. I get a -x squared, and I get a plus 1, all on x squared plus 1 squared. So I'm interested, again, let's let this soak in. I'm interested when the slope is 0. Slope is 0, slope is 0, slope is 0, slope is 0. Those might be max or min points. Not necessarily. Or where the slope is undefined when the denominator equals 0, might be a cusp. Now, this denominator is never 0, because I get a positive when I square, plus 1 squared. It's going to be a positive number. So all I'm interested in is when is the slope 0. Therefore, I want to set -x squared plus 1 equal to 0. And I think we can see pretty quickly. Add x squared to both sides. I get x squared is 1, or x is plus or minus square root of 1, 1. So normally here, I would be finding f of the endpoints. negative infinity, f of infinity, but I can't find those. We never get to infinity. It's just a concept. It's not a number. Then I'm going to try f of 1 and f of negative 1 and see those values. That's where the slope levels off. So when I put in 1, I get 1 on 1 squared plus 1. I get 1/2. When I put in negative 1, I get negative 1 on negative 1 squared plus 1. I get negative 1/2. I notice if I put in 0, I get 0. 0 gives me 0 on 1. I'm going to go to a quick graph of this. So I've got these points. Now, this is powerful, important for us to realize. Not only does the graph level off at these 2 points, it is the only place the graph levels off. So, does it come up, level off, and go up forever, because it never levels off again, then maybe come down, level off, and then proceed down forever, so these are just stationary, or does it come up and then come back down? Well, what did we determine with the big X test? This graph, eventually, the 1 doesn't really matter. Eventually, it wants to look like x on x squared, so eventually it wants to look like 1 on x, and eventually, when x becomes a billion, we got basically 0. This is going to get sucked into 0. And this is going to get sucked into 0. Therefore, our max occurs at 1, and it is a maximum of 1/2, and our min occurs at negative 1, and it's a minimum of negative 1/2. Now, quick quiz, is this a local max, an absolute max? Is this a local min, an absolute min? And the answer to all 4 of those questions should be yes. This is local and absolute max, local and absolute min. Okay, so that should keep you busy. You'll have plenty of examples just like that. I believe these are some of the problems that are some of the odd problems, and so if you're looking for more practice, you certainly have it here. Make certain that you're given some discussion along the way of some decisions or some ultimate answers you get. Make sure you are always considering what the domain is if it is not given for you, because sometimes we have some points to consider, such as on see what problem was that? This last one, we had to consider negative 1 and 3, the endpoints of our domain that were it was just implied, it wasn't stated. So endpoints, stationary points, points of non-differentiability, all of those can be our max and min. Good luck to you. Take your time on them and double check, make sure you're checking all of your solutions. There's another section of 5.1 to follow.